think I opened it. There we go.
Okay, you're going live.
Yeah. Okay.
So hello everyone and welcome to the Geoscience and Geoenergy webinar of 16th of December 2021. So unfortunately Hadi could not make it today and that's why I'm here. So my name is Maartje Boon. I'm a colleague of Hadi at TU Delft and together with Sebastian Geiger from Harriet Watt, I have the pleasure to co-host today's webinar. So we are delighted to host Ahmad Sami Abushaikha from Hamad bin Khalifa University as our distinguished speaker. So Ahmad Sami Abushaikha is an associate professor at the College of Science and Engineering at Hamad bin Khalifa University. His research interests are reservoir simulation, fluid flow in porous media, discretization schemes, high performance computing, petroleum engineering, and enhanced recovery mechanisms. Before joining Hamad bin Khalifa University, he was postdoctoral fellow for 2 years at Stanford University. In 2014, he received his PhD in petroleum engineering from Imperial College London, and he has a master's in reservoir geosciences and engineering from Institut Français du Pétrole, and a bachelor's in petroleum engineering and economics from UT Austin. From 2004 to 2009, Ahmad worked at the Qatar Petroleum and Total Research Center at Pau in France. Ahmad is the founder and team lead of QSAR, which is the first subsurface modeling and simulation research group in the region. The QASR group is dedicated for research, development, and application of new methods for the modeling and simulation of subsurface hydrocarbon reservoirs, with focus on carbon reservoirs and giant fields. So thank you, Ahmad, for graciously accepting our invitation. And to the audience, please note that this lecture will last for about 30 minutes, followed by questions. And please type your questions in the chat box, and Sebastian will take them after the lecture. And please do not wait till the end of the lecture to post your questions, but just type them whenever you feel appropriate, as they may trigger other questions by other participants. So Ahmad, we are all very much looking forward to hearing your lecture, so please start.
Well, thank you very much. First, I'd like to thank you and thank, of course, Sebastian and Hadi for inviting me in this excellent webinar. It's been wonderful months watching other people's presentations and webinars, and it's been a very good learning experience. And I'm truly honored and delighted to be here to discuss some of our humble work that we've been doing for the past 2 to 3 years. As the title says, here we're delighted and humbly say that we became part of the Billion Cell Club for Reservoir Simulation. And this humble presentation today that I'll be discussing with you will discuss the challenges that we faced in joining this club and how we overcame some of them and some of the successes that we're very happy to share with you today. So first, I'll start with you with a small background where we come from and why we decided to take this challenge. So we come from a region that holds more than 50% of the oil and gas reserves in the world, and most of them are actually carbonates, and a lot of them are gigantic and very large oil and gas fields. For example, if you look at the state of Qatar, where we come from and our university is part of, is the North Field and the South Pars field. Both of them are the same geological field, but they're only divided by the political lines. So this field is about 9,000 square kilometers and holds more than 1,000 trillion standard cubic feet of natural gas and non-associated. Another giant oil and gas field is oil field. I apologize. Is the Ghawar field in Saudi Arabia, which is extremely well known. Another one is in Kuwait, the Borgan field, and of course in Iran, the Hawas fields, and also some other fields in UAE and Oman. And that was our main challenge. We wanted to develop a reservoir simulator that's capable of modeling really the physics and the geometry of these really complex oil and gas fields. So we went ahead and started saying how we can develop something for that region. But before I go here, I'll discuss with you some of the workflows that goes on any oil and gas company to solve or to model some of these problems that they have for the oil and gas systems. Any oil and gas company, they have a reservoir engineering department or a geology department, and they both work hand in hand in developing their assets. So they start first with a geological model, then after that they upscale it to a flow model, then they run the simulations and they compare it with the real data that they get from the field. And there's an iterative process that happens between the history matching or the data matching between the real data and the flow data. And that heavily depends on the reservoir simulator itself. So why is that interesting? First, any reservoir simulator in the world, it solves a very simple equation. Just like the physicists around the world, they use E equals mc squared. In reservoir simulation, we face a similar problem, which is the ax equal b. So all of reservoir simulation does it is to try to find the solution for x. And what does A have, as you can see here on the right hand side, is the geological properties and the connections for the flow between these cells inside the reservoir simulation. So unfortunately for us, we don't know A. If you look at the figures in front of you, if you're lucky, you only have 400 or 600 data points, and these data points come from the wells that you drilled. And the depth of investigation of these data could be in centimeters, meters, or if you're lucky, a few hundred meters if you use well testing. So you have 400, 500 data, you don't know A, you try to solve X, and B is basically your mass balance equations or your constraint equation. So you're dealing with a huge amount of uncertainty. And oil and gas companies, they try to solve this problem to find the dynamic data, such as pressures, oil in place, and how to find the optimal strategies. You can see there's so much uncertainty that we're dealing with, and actually solving AX equals B is not as intuitive as it looks. So a reservoir simulation, well, it's if you want to put it in one sentence, it's with the way we can look at it. It's the crown jewel for oil and gas reservoir engineering departments. They collect all the data, then they put it in the simulation systems or models, and they try to find the optimal strategies to develop their assets. And they could run hundreds or maybe thousands of simulation models to find these optimal strategies. And the simulation systems or the softwares, they are underpinned by many physical concepts such as the conservation of mass, the fluid phase behavior, and the Darcy equation for the fluid flow and porous media. So all this data they input inside the reservoir simulator, and they try to find the best way to develop their billion-dollar assets. So there's a huge amount of risk, and they really need to find the best reservoir simulation system that is able to model their assets. So we took this challenge. We said we want to develop a specific reservoir simulator for giant oil and gas fields. So we applied for funding in the spring of 2017 to the Qatar National Research Fund, and luckily we got the funding. This funding was in collaboration with Delft University and Stanford University, and we wanted to develop a fully implicit MPI compositional reservoir simulator with the most advanced linearization and discretization schemes. And I will go about why we decided to go for MPI, why we decided to go for advanced linearization, and why we decided to go for discretization schemes, a high order. Now the simulator, we are in 2021, and it's at technology ready level 8. And also we didn't want to reinvent the wheel. We know there's a lot of code out there that can help us for the pre-processing and post-processing steps. So we were lucky to have used the Inmost toolkit for supercomputer capabilities, Inmost, developed by Kirill Turikov from Russian Academy of Sciences, which we used it to do a lot of the background work for us in the simulator part, and we focused more in the linearization and discretization and the physics part. So I'll just walk you through some of what happens into an oil and gas reservoir before I go to the challenges that we're facing. Usually there's a life cycle of oil and gas field, usually there are 3 phases. The first phase, which we all know is simple one, the primary recovery, where oil is produced from the wells through natural drive or water drive or a gas cap, for example, or solution gas drive. Then after the pressure depletes and the oil and gas company does not want to go below the bubble point, for example, for oil field, they would go for secondary recovery where they would inject water to maintain the oil pressure above the bubble point and to actually push the oil out. After that, there's the tertiary recovery, which involves thermal methods, gas injection, or chemical flooding for changing the viscosities of the system and the rock interaction between the fluid and the rocks. So for any reservoir simulation technology or a study, there's large amount of uncertainties, and there's a lot of scenarios that need to be optimized. So this reservoir simulator is used for risk analysis, for finding optimal strategies, and to find a way to reduce the uncertainties in the underground. So there are many reservoir simulators. Maybe I think there are 10 or maybe 12 all around the world. There's the darts. We can define them into two different categories. The research simulators were developed by research institutes and universities, and the commercial simulators are developed by companies. For the research simulators, we have DARTS, developed by Denis Voskov from Delft University, ADG Perez from Stanford, UT Chem, UT Austin, IPARS, UT Austin, and Qasr us at HBKU. Of course, the usual suspects, the commercial simulators, such as Eclipse and Intersect from Schlumberger, CMG from Computer Modeling Group, and T-Navigator from Rock Flow Dynamics. And of course, Echelon from for Stone Ridge Technology. So for us, when we started developing this software or simulator, we had three main challenges that we wanted to overcome. The first one, as I discussed with you at the beginning of the talk, is we are dealing with giant oil and gas fields. So we are going to be dealing with high resolution geomodels or high resolution flow models. So we are dealing with large grid numbers. So that's the first challenge that we're facing, the large number of grids. The second challenge is how we can model the complex geometry of the systems and the correct material properties, such as the orthogonality of the permeability. In this case, most of the commercial simulators, they use the well-known two-point flux approximation, which does not work for non-K orthogonal grids and unstructured grids. So that's another challenge. We need to find a discretization scheme that's able to model the fluid flow and the unstructured domains with the full tensor permeability accurately. The third challenge, since we're dealing with natural gas fields, and there's a new drive now to use CO2 sequestration for EOR and actually for storage, we are going to be dealing with complex EOR processes. So we'll be dealing with high nonlinearities. So that was our third challenge, how we're going to be able to model all these physics inside a Jacobian to solve the AX equals B with the large high linearities in the system. So to overcome these, we propose three ways to overcome them. The first one is parallelization. That should solve for us the large number of cells. So we decided to go for MPI. So we use domain decomposition to divide the large mesh into smaller subdomains, and then each subdomain gets allocated a different core to be solved. The second challenge is the linearization. That slightly solves for us the nonlinearities because we have control over the linearization of the equations. In this case, we adapted the technology developed by Denis Voskov, the operator-based linearization scheme. And with it, we're able to control the derivatives inside the Jacobian, and we can decrease or increase the nonlinearities depending on how difficult the problem we're trying to solve. The third one, for the non-orthogonality of the K grids and also the complex geometry of the grids, we adapted two different discretization schemes, the MPFA and the MFD. For the MFD, I've been working on this discretization scheme for the past 6 to 7 years, and we have lots of validation and publications that prove the implementation of this method for fully implicit systems and for compositional modeling. Now I'll go with you guys the architecture of the simulator. This work has been done by a postdoc, Dr. Long Li, who is currently associate professor at China Academy of Sciences. So our code, we can divide into 5 different parts: the mesh, the discretization, the wells, the solver, and the sim model. First, I'll go in each one of them and discuss with you the challenges that we faced and how we overcome some of them. So for the mesh, as I discussed with you earlier, what we do is we divide it into different subdomains, and we find out the shared cells. Then we create ghost cells for them to communicate between the CPUs that are being solved at in order to maintain the continuity of the calculation. So we take a mesh, we divide it, and we solve it at different CPUs using MPI library. As simple as that. So we implemented this and we tested it for a black oil model using our simulator for the SPE10. So we took a SPE10 model black oil, and we have 4 producers and 1 injector. And we decided to study the scalability of solving this system in multiple cores. So in this case, you can see that we tested it 3 different ways. The first one, we use 40 cores. Another case, we use 10 cores. Another case, we use 8 cores. All of them, that's per node. So we use 120 cores, and we start testing. If you use 40 cores, what would happen? 10 cores per node, what would happen? Or 8 cores per node, what would happen? So if we look at the blue line, that's 40 cores per node. So we're using 3 nodes in this case. So you can see it's not really linear. Semi-linear, we get about 90 times speed up. So it's okay, 40 cores per node using 3 nodes. The reason for this is because the cluster that we're using, it has 22 CPUs per node and 20 cores per node. However, the channels between the RAM and the cores are 4 channels. So that the calculation needs there's a backlog that delays a little bit the calculation process. So we went ahead and we tested 10 cores per node. In this case, we used 12 nodes. And you can see the speed up is getting better, about 113 per core. And then we went ahead, we did 8. So we got almost a linear scalability, about 118 for this case. So we're happy with this. We got fairly linear scalability for this model, but we wanted to test what's the minimum number of cells we can allocate per core and maintain that scalability. So in these figures, you can see in front of you, the lowest number that we're able to get away with about 9,000 cells per core. Just let me remind you here, we're using a black oil model, so 3 unknowns per cell. So this work was done just to see the limitation, and for this SPE10 model, I think it's about 1 million cells. We were able to get away with 9,350 cells. I think maybe 8,000 in another case. We were happy with this. I think there's room for improvement, but I think that's okay for now. So with the scalability test, okay, so we're fine. Let's move on. So then we went for the discretization. As I discussed with you, this is important for us to model the unstructured domains accurately and the full tensor permeability. So we employed the multi-point schemes such as MPFA and MFD. So I'll give you just a small overview about these methods. The TPFA is basically uses only 2 stencils between 2 cells to model the flow, and usually it has to have the interface orthogonal to the direction of the flow. And however, it does not work very well for unstructured grids and for full tensor permeability. The next scheme is the MPFA. It uses neighboring stencils to maintain the pressure gradient, and is able to model the flux more accurately. And in some cases, it does a very good job on unstructured grids and full tensor permeability. The same case for MFD, but what makes it slightly different, we use here also, we use the centroid pressures of the cells, and also we use the interface pressures of the cells. And we use an extra equation to maintain the continuity of the fluxes between interfaces. So in this case, the Jacobian would increase in size, in number of rows for the MFD. So what's good about MFD and PFA is they are fairly good for unstructured grids and for full tensor permeability. So we went ahead and did a small numerical analysis between these 3 different schemes to understand their behavior. The first row, that's the MFD. The second row is the TPFA, and the last row is the MPFA. In this case, we are comparing on the left side a discrete maximum principal analysis, and we have a Dirichlet boundary condition at the centroid of the mesh, and we have a rotated permeability for the full tensor. And you can see that the MFD does a very good job in taking the direction of the permeability, where the TPFA, the central, does not do a good job. However, for the MFD and the MPFA, you can see it does not really respect the discrete maximum principle, and these are the red dots you can see here. That's where the TPFA does a fairly good job, but does not model the flow very accurately, where it maintains the discrete maximum principle. So after this numerical answer, we applied it for a real case. So we took the SPE10 and we made it unstructured. So we took the top five layers of the SPE10 and we made it unstructured. And we tested the three different discretization schemes under all the same conditions. We have four producers here and one injector. And you can see here the blue color is the MPFO, and the red color is the MFD, and the black color is the TPFA. So you can see that the MFD and the MFD and MPFA, they model the flow fairly similar to each other, especially the water cut. You can see the TPFA, it models the water cut much earlier than the MFD and MPFO, all for the same cases. And where the MPFA and MFD, they model the water cut and also the oil rate more similar to each other, and not and TPFA does not model it as accurate as them. So that's a good validation for these schemes for unstructured grids, and it shows how the TPFA does not do a good job in modeling unstructured domains. So that's another challenge that we overcame, and we're happy with this. Just to remind you, earlier we overcame the issue of large meshes, and now we overcame another issue or a challenge, which is modeling the flow accurately in unstructured grids. And for the tensor permeability, that's also another case where we rotated the permeability in this egg model here. And you can see the TPFA does not model this case very well, does not model the direction of the flow. And of course, the TPFA does not model it, or there's a big discrepancies between the oil rate and the water cut between the MPFA and the MFD. So that's two challenges that overcame. We're happy with. Now I will move with you for how we represented the wells inside the simulator. Here we didn't do much anything different. We just used the standard well models developed by Long Lee, my postdoc, and the multi-segmented wells. So for the multi-segmented wells, we represent them with different well bodies, and each well body would be communicating with different reservoir block. That's a nice case that I would like to discuss with you here, is a condensate banking case, where oil saturation starts building up around wells on natural gas fields. So here we have a vertical well, and the one to the right is a deviated well. So we're able to model vertical wells and deviated wells no problems, and model some of the physics around them, such as condensate banking. That's for the standard well models. For the multi-segmented, also we can connect two connections with another vertical connection, as you can see here. Also the condensate banking building up around these two sections of a multi-segmented well. So here we didn't really face much challenges. We've tried to focus more on how we can solve the large meshes faster, and also the discretization schemes. For the solver, we also faced another challenge. For the nonlinear solver, we used the Newton-Raphson method. However, for the linear system, this is something that we still under research, and also we're facing challenges in it. Currently, we're using an iterative solver that solves the whole Jacobian all at once. So we treat the whole Jacobian as one block, and we just solve it, regardless of the type of physics and regardless of the type of discretization, such as the TPFA or the MPFA or the MFD, where number of stencils could be different, and also the number of equations can be different. So since we believe we are one of the first people to implement the MFD into reservoir simulation for real-world problems, we've been doing research, especially my PhD student, Stefano Nardin, in developing a specific linear solver for MFD. So here we've been developing a special preconditioning technique to order to accelerate the process of solving the MFD. What makes it slightly different, as I discussed before, than the MPFA is now we have a secondary equation, another equation in the Jacobian, which is the momentum balance equation that assures that the flux is continuous. So we have two blocks system now that we deal with, as you can see here. One for the mass balance, another one is for the momentum balance equation. So we've been doing some research here, and we've been successful in modeling dead oil cases without gravity, and we're also doing some research about that with gravity, and after that we move to black oil and compositional. So that's a challenge that we're still facing, is developing linear solvers specifically for our needs, and that's a research question that we're still working on, but so far the linear solver we're using is fairly capable. Now I'll go to the sim models, the physics that happens in the subsurface subdomain, subsurface oil and gas fields. I'm sorry. So we have five different simulation models or physical models. First one is the single phase, which models water flow, such as water storage or disposal water storage wells. Another one is dead oil. Third one is black oil. The fourth one is compositional, and the fifth one, sorry, is the three-phase flash. So all of these, I think most of you would know about. What we've been working on a lot, especially my PhD student Abdussalam Abd, is that with the oscilloscope is the three-phase flash. This is very important for us. Um, as I mentioned, I think maybe in the beginning, that our countries is now going through the they stated that they will capture between 5 to 7 million, ton of CO2 per year for CO2 sequestration purposes. So this is fairly important because we wanted to know what would happen if we inject CO2 into a depleted oil field with some water in it, and where would the CO2 dissolve, in the water phase, in the rock, or it will be suspended in between the pore spaces. So that three-phase flash library that we're developing now will able to help us with that. So to discuss it in a simple terms, in a three-phase flash, you would like to know which components are in the vapor phase, which components are in the liquid phase, and which components are in the water phase, and which one's dissolving within the water or the liquid or the vapor. So we developed a stability analysis case coupled with negative flash as one approach in order to find out how much of that CO2 would dissolve inside the water for CO2 sequestration purposes. So to test it, we tested in one layer of SPE10, and here we're injecting pure CO2 and also a mixture of 50-50 between water and CO2. And this work has been published in RSC. And here you can see where the CO2 is dissolving inside the water. So in a case, if we only use two-phase flash, basically the CO2 would not be dissolving inside the water. And that's something is very interesting for us because we would not like to know how much of that CO2 would actually stay inside the water. After how many years? How would that help the CO2 sequestration technology in understanding in storing the CO2 for tens or 20 or 30 or maybe hundreds of years? So that's an important library that we're working on, and hopefully by the summertime we'll be able to deploy it and test it in real cases, hopefully maybe 6 to 9 months from now. So after all these challenges and the overcomes that we slightly overcame, for any company that we go to present our work, they always ask us the following question: how does this simulator compare to another legacy simulator, to a legacy simulator? So we went ahead and we basically benchmarked our code to see how it performs versus other legacy simulators. So this is one case that I would like to share with you where we compare our simulator to a legacy simulator. It's a SPE10 top 5 layers, black oil model, four producers, and a center injector of water. The water injector is a constant rate, and the bottom hole pressure and the producers are constant bottom hole pressures. And as you can see here, the red color is the gas-oil ratio, the blue is the water cut, and the green is the oil rate. And we're able to match it exactly. So this was a nice step for us. After overcoming the challenges that we had earlier, we're able to also match the legacy simulators available in the market now. Just let me mention here that we use here a structured mesh However, we have other cases where we use the unstructured mesh for both our simulator and legacy, where our simulator performs better. But this is a topic for a different presentation that we're going to present in the WIPIC workshop in Qatar in March, and also we're presenting this in other conferences over the summer of next year. So now let's go back to the other main challenge that we had in ourselves. When, of course, the pandemic hit, most of us were stuck at home, and we decided to take another challenge on ourselves. So we said, why don't we try to model a billion cell simulation? So we said, okay, let's do it. So we went and we looked at what people have been doing for the past 10, 15 years in modeling these billion cell simulations. Of course, who's been a champion of this for the past 12, 15 years is Saudi Aramco. I think the first case they ran it 2009, another case they also ran it on 11, where the runtime, the first case was 4 years and 4 days, I apologize, and another case was 21 hours using 3,000 wells and close to more than 1 billion cells for production simulation of 60 years. Then Schlumberger, I think in 2014, they ran Intersect for production period of 20 years, and it ran time for 10 hours. And I believe this was a compositional case, and they used close to 300 servers. And of course, ExxonMobil, they ran a few cases, I think, a few years ago, and they used close to 1 million cores. And another company or another simulators, Echelon, developed by Stoner's Technology, they used a different approach than us and Schlumberger and Saudi Aramco. They used GPUs to solve their system, and they used 30 servers, about 120 GPUs, and they did a very good job in doing a runtime of less than 100 minutes. So for us, our 1 billion case model, we took the SPE10 top 5 layers, and we made it unstructured, as you can see here. And we made it into 44 kilometers and 22 kilometers in the Y direction and 20 meters in the Z direction. We used 1 billion, 14,816,000 cells, 108 wells. Simulation time was 20 years. The maximum time stop we used was 10 days, and we used 4,600 cores. So 115 nodes, each with 40 cores. Remember earlier where I discussed with you the scalability of our simulator, and it showed that it's better for us to use 8 cores. We wanted to use 8 cores, but unfortunately we only had 120 nodes in our cluster, which is also a good number of nodes to have as a university. But we couldn't use 8 cores per node because we need much more nodes for that, and we don't have the capacity for this. So we used 40 cores. Hopefully, if we have access to another cluster in the future, we'll go for 8 cores. Another shortcoming or something challenge that we faced, we couldn't run the MPFA or the MFE because they require more memory. So in this case, we only ran a TPFA. The simulation time, it took less than 36 hours. So we were happy with this. Of course, there's room to improve and room to optimize this. This was our first run, and we're happy with it. So just to show you the simulation time, it took about more or less 36 hours, and this is the CFL case, CFL infinity number. Shown in this figure, and we stretched it a little bit for visualization purposes, and here you can see the gas saturation around in the field after 20 years of simulation. So after this, we went and discussed this with our funding agency, the Qatar National Research Fund, and they were very happy for this. This was a nice success story for them, and also a nice success story between us and our collaborators, Delft University, Stanford, Russian Academy of Sciences. Because we all started working on this in the summer of 2018, and we worked very efficiently with each other, and we were able to achieve this. So we had a nice press releases in Qatar and regionally and a little bit internationally, where made our funding agency happy about this success. So here I'd like to discuss with you some challenges, actually, more of engineering challenges that we faced during modeling the 1 billion cell case. The first challenge is where do we, a pre-processing challenge. Where do we um do the domain decomposition? Do we do it on the cluster or do we do it in the local workstation? So if we did it in this cluster, okay, fair enough. That will take a few hours. However, how can we visualize it? We have to transfer it from the cluster to our workstation and check it. So we said this workflow maybe will not work for us. So we decided to actually do the domain decomposition and the subdivision of the mesh locally. So we'd run it locally, it'd take maybe a day or two because it's a smaller machine. However, we're able to visualize it better and we're able to check if everything is okay. So we would do the domain decomposition locally, then we would send it to the cluster. In that case, we save a lot of time. If we run multiple cases, we don't have to keep dividing it. So that's one thing we faced and we overcame it with that. Another challenge is the load balancing between the subdomains. So in this case, some domains, some subdomains, they would have 50,000 cells, for example, and other ones would have 150. So the ratio will be around 3, sometimes 2.5. So that's a question that we need to work on, how we can make sure we have a small load balancing ratio between the cells. Because if you have a subdomain with 150, another subdomain with 50, that means some CPUs have to wait for the others to finish the calculation, then do the transfer of data. So that's a question of research that we would like to maybe focus on in the future. Another issue we solved is the wells intersecting the subdomains. So we need to make sure that our wells, they don't intersect the subdomains during during the division process, or the simulation will fail. So each well has to be contained in only one subdomain. I think Long Long was able to develop a method to actually draw the subdomain around the wells, but we need to slightly optimize this, or we just need to just put the wells inside the subdomain. So that's also another research question, a challenge that we need to work on, how we solve the wells intersecting the subdomains for the MPI calculation. Another challenge that we faced is the visualization of the 1 billion cell case. So we did the calculation, we're happy, everything is fine, everything made sense, but we wanted to visualize the 1 billion cell case. So we took the data and we put it in our workstation, and it basically didn't want to load all the data. So it only showed us maybe 60 or 70% of the subdomains. We just didn't have the memory capacity to view it. So Kirel and me, we worked together and we said, okay, let's try to install ParaView server inside our cluster. So that's what we did. And let me give you an example. For us to load the billion cell case, which not most of it, let's say 60, 70%, it took like 3 hours, 4 hours to load in our workstation. Then we went ahead and loaded ParaView server inside the cluster. Then we had to run it on the cluster, then create a link between the cluster and the ParaView local client, and visualize it locally inside the workstation. So it wasn't really a very easy thing to do. It took us a few steps, and it's not very intuitive. So we were able to do it. We used 3 nodes for visualization, and it took 8 seconds to visualize. So that was fantastic to see, but you're using cluster time during that. So that's something you have to do if you run really large models. I'm most probably going to use clusters for visualization. So before I go to the conclusion, of course, I have to thank the Qasr team for their hard work. This would not have been possible without their hard work, the hard work of Long Long, Abdussalam Abd, Stefano Nardin, and also Nazang, and also our support from the industry, the college, and the SPE director. Also, he's in the picture. I would like to thank all of them for their commitment and their hard work. So, in summary, this presentation shows that modeling or simulating large models are becoming somehow of an easy process these days. with the advances in the libraries available and the advances in computational power. What's next for us is we want to focus more into reactive transport. What would happen if you inject CO2 and the interaction with the rock? That's something of our interest for the CO2 sequestration projects. And also for us now, our simulator is a fully implicit simulator. As we add more physics, especially as we move with the three-phase flash and maybe geomechanics in the future, maybe we would like to focus a little bit on sequential full implicit, where we divide the Jacobi into different parts and we solve each one inside the nonlinear loop independently. Another thing is history matching and also quantifying our uncertainties for risk analysis. That's something we would like to work on, hopefully next summer. Before I thank and I finish the presentation, I'd like to mention that we also have 2 PhD openings, one in our group, one in Reservoir Simulation, another one in Reservoir and History Matching. So if you're interested, if you know anybody interested, please go ahead and email me on the email shown here. Before for the acknowledgement, of course, I have to thank our funding agency, Qatar National Research Fund, for supporting this project. Of course, the fantastic work that has been done by the Qasr team. Of course, our collaboration with Dennis Boskov, Marquette from Delft, Kirill Turikov from RAS, and Hamdi Chalapi from Stanford. With this, I would like to thank you all for your attention. And now we're open for questions. Thank you very much.
So thank you very much, Ahmad, for this very nice and detailed description of the simulator of your group. I saw that there are several questions coming in. So Sebastian, please go ahead.
Yes, thank you very much also from my side, Ahmad. And before we sort of take over, just can you see us all now? Just unshare your screen. I think that should.
I share. Okay. Yeah, sorry about that. Yeah.
Then you can see Martin and myself. Before I put the questions from the there's actually the question just came through that I wanted to ask you. Is Quasar an open source code? Can other people use it and add their new physics to it easily?
It's to be honest, it's not an open source. And adding physics should be okay because we're using OBL, so you don't have to worry a lot about finding the derivatives of your equations. It's not an open source. I don't think I'm planning to make it open source, but we are planning to maybe making a dead oil simulator of this simulator open source.
So because it's commercially too sensitive that you.
Yes.
Okay.
So maybe I'm thinking, we need to discuss it as a group, but I'm thinking maybe we'll create an open source for a dead oil model, for example, with a limited number of cells, maybe 1 million or something like that. Yeah. Then, of course, a clever guy can go and make it into 10 million.
Yeah. Wilhelmine ask a question, says, thank you for the nice presentation. What would you consider as the biggest challenge overall during the development of the simulator? You spoke about many different challenges. What was the
motivating the team? That was very, very difficult, especially during the pandemic. So it's just keeping everybody focused because I was lucky enough to have very smart people in my group. And each one with them, I was focused on different parts. One for physics, one for linear solver, another one for the OBL, another one for the three-phase flash. And each one would work independently. Then towards, I think last year or 2 years ago, they started working together and putting the simulator together. So keeping them motivated and working together, that was quite a challenge. But then it worked out. Yes.
Okay. And from technical side, so of the technical challenges,
yeah,
there's always a human challenge to keep a team motivated.
Okay. Technical side, I think could be just maybe the MPI. Just making sure the subdivision is done correctly and the communication between the subdomains is done correctly. That would have been a challenge. Yes.
Yeah. Thank you. So continuing to discuss the challenges for a moment. So George Costa Gomez said, very interesting talk. Work, thank you. And his question is, answered a little bit on this already. You said, how is it to build a billion cell reservoir model, manage all the data, and then visualize the simulation output? Were there additional challenges that need to be overcome? You talked about the simulation output side, the visualization side, but actually, how do you create a billion cell model? Do we have the data? How do we
Yes.
manage the data?
So for this, Kirel and me, we basically took SPE10 and we made it slightly unstructured, and we basically made it bigger. That's one thing that we did. We didn't use actual, like, but the data that we use is SPE10. So the permeability varies between 0.1 to 30,000. So it's a very large variation. And also the porosity varies between 0.01 to 0.5. So that's also a very difficult problem to solve. We didn't have a problem with the large data, thankfully, because we used InMost, developed by Kirel. So a lot of technical work background that we didn't need to focus on. So thanks to this library. So we mostly focused on the physics part. So that's thanks to the InMost library, to be honest with you.
Yeah, staying a little bit on the challenge side, there's some questions around sort of some technical aspects of your work.
Yeah.
So Timur Guy, Professor, questions: It is difficult to commercialize any research code. What is the future of the code? Are you planning to extend and use it as a reference for challenges such as CCS, or use it as a research platform?
Well, I know Timur. He was with me in Stanford, so I think anyway. So yes, we're planning to actually commercialize it. We applied for a provisional patent a month ago or 2 months ago in the United States, and we would like to commercialize it. And we know it's going to be a challenge, but I think in our region, I think there's demand for this, especially with the move towards CO2 sequestration. So I think the market. I had a discussion with a colleague of mine. And I said the reservoir simulation market is about 500 million or $500 million market, and if we're able to capture 1 or 5% of that, we'll be happy.
Yeah, there's a goal. It's nice to think about what is the size of the price there. Diving a little bit into sort of some of the technical aspects of your work. So Ali asked, and thank you for the good talk. There's a big difference between TPFA and the two extensions if you go to field scale simulations where the heterogeneity increases. And then he actually has a follow-up question, says, what are your thoughts on two questions? What are your thoughts on adding fractures to your simulation, dual porosity, dual permeability models?
I do believe Long, who also developed the simulator with us, he implemented fractures. But I haven't tested it. I don't think we have tested it extensively, but we added fractures as a volume. So we do not treat it as a discrete fracture model. We treat it as a normal cell with different properties. But I haven't tested it. That's something that we're going to work on for early next year. Yes.
Okay, and so there's also no extension to dual porosity, dual permeability model, because you looked for your masters, you looked extensively at how well do different transfer functions work.
Maybe. I mean, we're a small group. There's a lot of work to be done, but yeah, maybe. But so far, we focused a lot on the physics, especially the compositional and the three-phase flash. Then maybe we'll go for dual porosity. But yeah, step by step. Yes.
So Ali, who asked the question, just finished his PhD with me not too long ago. And he's a dual porosity modeling expert. So if you need help and he's going back to the region, there's someone who's probably always happy to collaborate. Coming back, here was another technical question from Rahil Ahmed. Sorry, I need to go this way. Thank you for the very interesting talk. Are you focusing on any specific problem for linear solvers, and what kind of preconditions are you developing?
Yes, we are focusing on linear solvers for MFD, for magnetic finite difference, and we are focusing on linear solvers that are able to solve different blocks inside the Jacobian. So they are mostly going to be physics based. So we make sure that they can solve black oil with gravity, composition with gravity, and capillarity, and of course three-phase flash. So they're physics-based preconditioners that are mostly focused for block problems.
Just on that note, I remember a long time ago I looked a little bit at linear solvers myself. So why, and you're much more attuned to the problem, but why not simply use something like the SMG solver, linear solver as a black box, which is parallelizable already, and simply run it out of the box? So why is there a need to develop linear solvers yourself?
That's a very good question. Because some of the AMGs, they're not open source, I believe.
No, it's not.
Yeah, so we cannot really compile it in our code. So we wanted, first, it was a research question. We wanted to develop a linear solver for the mimetic finite difference, and we wanted to keep our own code with us and able to scale it for different problems that we're facing. Yeah.
Okay, yeah, that's of course absolutely fine to say.
Yes.
If you have a good research question to think about how you do design your own linear solver that's optimal for that problem.
Yeah.
Another question from Ali, and he refers to the table that you shown on slide 33 and wonders how similar are the different hardware architecture CPUs for comparison of the billion cell models. And you talked about some of them. You mentioned one way from 2014 and how the hardware has evolved over time as well.
Yeah.
So how fair, I guess, how fair of a comparison is that table?
It's a very good question. I think, yeah, it is unfair for us to compare a work that's been done 7 years ago. But that work has been done 7 years ago, and I don't think any work has been done since then, apart from Stoneridge Technology and ExxonMobil. ExxonMobil, they used close to 1 million cores, but they didn't share the runtime, simulation time. But I believe it was probably minutes or maybe 1 hour, a couple of hours. But that's a start for us. As I mentioned, we're a small group. We're quite competitive and ambitious, and we're planning to scale a little bit, maybe for more billions of cells, and use a larger cluster to speed up the process.
And it just, again, so interest question from my side. So for someone who just thinks much more on the smaller European reservoir side, if you go to a billion cells, what is the typical grid block size in
this case, what we use was 44 kilometers by 22 kilometers, so the grid size about 2 meters.
Okay, so very small.
Very small. Yes, yeah.
Taufik Nassan asked, did you build everything from scratch? How many years did you spend until you reach the current status? And what is the coding language that you've used?
Thank you. Yeah, no, we didn't build everything from scratch, of course. As I mentioned before, we used Inmost a lot in our background work, from uploading the mesh to outputting the mesh to also getting properties inside the Jacobian from the mesh, for example. For the code, we use C++. I forgot what was the rest. Yeah.
How long? Which coding language?
We started summer 2017, so about 4 years now, something like that. Yes.
That's really impressive.
Yes.
Do you run it with a GUI, or is it everything is scripted?
I don't understand. What do you mean?
Do you have a graphical user interface for your simulator to set things up, or is it also scripted with?
No, we run it as an input text file, and the visualization we use ParaView.
Okay.
So running it, no, it's mostly like you run it in MS-DOS, like MPI ESC.
Yeah.
Then you run the function. But for the visualization, we use ParaView. The input data is very similar to any legacy simulator input file. So it's very intuitive. By putting the properties, loading the mesh is very intuitive, similar to any legacy simulator.
Yeah. So thank you. So speaking of legacy simulators, so there's another PhD student who worked with me and just had his defense very recently. Josh has heard what is releasing a very realistic open source carbonate reservoir model would be great to be used in your work testing. This billion STOIP, millions of cells, so not billions, but millions of cells, over 400 wells in 30 years production. So there may be, it's not a billion cell model, but it's certainly sort of more realistic for the Middle East. And there's some further statistics. George is just putting through 24 CPUs in parallel with 22 million cells. Took me 28 days to run, 30 years production. Grid blocks are roughly 60 by 60 meters. Would love to do a test in an accelerated way. So it's all open access model. So you may want to get in touch with each other.
I just have a question. The mesh, is it conforming or is it the corner point geometry or?
The corner point geometry.
We're capable of converting it from corner point to conforming because we're using conforming geometry. But there could be some small bugs. But let's see. If you can share the mesh with me, I will convert it and hopefully it will work. Yes.
Okay. So I think George is on the line here. So you kindly shared your email address.
Yes.
So it's very best if the two of you get in touch, and then you.
A nice project.
Don't see any other questions coming through at the moment. Hold on. No, there's just one. Yeah, George says excellent. So probably do expect an email from George coming in the coming days. And here's another comment.
So sorry.
Just saying, congratulations for the fast progress. Yeah, go ahead. Sorry.
Oh, sorry. I thought. So I have a small question because you said you have a specific focus on carbonate reservoirs, right? So what makes a carbonate reservoir so different for your simulations?
The high heterogeneity. So we focus, and also the tensor permeability. So yeah, you're right. Maybe carbonate is a more of a category that we're using to market ourselves, but maybe sandstones also, of course, we can focus on. But most of the region in Qatar are mostly carbonate, and they're highly fractured, highly heterogeneous, and highly unstructured. Yes.
Yeah,
is that clear? Or yeah, I think she's muted.
Oh, yes, thank you.
You're welcome.
I think the other interesting challenge is the reservoirs. That's why I asked about the grid size model. Some of the reservoirs are so gigantic, just dimensionality is so big that if you go with 10 million grid blocks, you still have a kilometer by kilometer grid block. And you think about all the heterogeneity that's.
Yes. So we want to capture most of it. But as I mentioned earlier also, I mean, in any field, you only have 300, 400 points of data. And these data, they come from the wells. And the depth of investigation for each data point could be 1 meter or 2 meters if you only use well logs without well testing. So you're dealing with a tremendous amount of uncertainty also.
Which you want to history match and you're running not just one simulation, but the same over and over again.
Exactly. Yes. Yeah.
I think there are no further questions coming through from my side. So Ahmad, thank you very much for your presentation and for really tackling a tremendous challenge within 4 years through a pandemic, writing very impressive piece of developing very impressive piece of software. Thank you to our audience. There's one I'm just going to give you, because we have 1 minute left. So I'm just going to give you that final question. In carbonate rocks, could you consider as well karst systems in your model representation?
So I would assume a karst system here. I mean, Vaghi fracture.
Yeah.
So basically, I think yes, because we're modeling the fractures as a cell, as a volume. So we could basically make the porosity 1, for example. So it should be okay. But we haven't tested it. But in theory, it can be represented, yes.
So yeah, thank you for allowing me to slip in that final question. So thank you very much, Ahmad, for a really interesting talk. Congratulations on this.
Thank you very much.
A big achievement.
Thank you very much also.
Thank you to our audience for some great questions. And that was our very last talk of the 2020 webinar series. So we see each other again in 2021. It feels like 2022. We see each other in 2022. That was the last talk of the 2021 series. Martje, over to you for some final comments.
Yes. Yes, thank you very much. So this was indeed the last webinar of 2021, and we will resume again on January 13th in 2022. And we will then host Nicole Dopfel from Norcy, who will speak about microbes in the subsurface, makers and breakers of energy systems. So I would like to wish you all a very happy new year and, of course, a nice break. And as Hadi says, stay happy, healthy, and tuned in to our Geoscience and Geoenergy channel. And we hope to see you in the new year. Thank you.
Thank you, everyone. Thank you. Bye-bye.